Good day and welcome back for the third part of our discussion on evaluating trig integrals. In this video we are going to pick up exactly where we left off in the previous video, where we evaluated two concrete examples involving integrals of tangent to a power multiplied by secant to a power. And at the end of that previous video, I left you with the challenge of coming to problem number 3 and seeing if you could complete this general strategy for evaluating integrals of this form when the power of secant is even or the power of tangent is odd. So let's go ahead and summarize together and fill in some details. Similar to comments I made in our first part of this discussion with powers of sine and cosine, it's not necessarily about memorizing how this works, but understanding the basic idea. So what we saw on the previous page is if we have an even power of secant, what we would like to do is pull off one of those even powers of secant and save it to play the role of our du. That requires us to rewrite this a bit algebraically. Note, in general, if you have something raised to an even power, say to the 2k, you can rewrite this as that thing raised to the 2k minus 2 plus 2. And using properties of exponents, you can write it as that thing raised to the power 2 times k minus 1, which is the 2k minus 2, multiplied by that quantity squared. This is why having that strong algebraic base is really important. So we're using our properties of exponents. So back to the integral. Our strategy is to pull off a secant squared. And as we noted above, we can rewrite secant to the 2k power as secant squared raised to the power k minus 1. And note, that's corresponding to something to the 2k minus 1, and then multiply it by that something, secant, squared. And this is really the template that we have for our approach. We are going to have the secant squared dx be our du, which means u must be tangent. So to get everything written in terms of tangents, we now simply rewrite this secant squared x as 1 plus tangent squared. And if we ever have an even power of secant, this is the approach we can use to evaluate the integral. So as stated as concisely as possible, we pull off a secant squared, use the Pythagorean identity to rewrite the remaining secants in terms of tangents, and we substitute u equals tangent of x. Note, if the power of tangent is odd, our second example on the previous page, we can apply a similar strategy. In this case, we're going to steal or borrow one power of tangent and one power of secant. We're saving them to play the role of our du. So in this case, we could say tangent to the 2k plus 1 is tangent squared to the kth power. That would be the 2k part. And then we're going to save a tangent for part of our du. Similarly, we're going to say secant to the nth power can be secant to the n minus first power times secant. So with this in mind, our du is going to be secant tangent. So u is secant. And that tells us every tangent needs to be rewritten in terms of secant squared. And note, from the Pythagorean identity, we can do so as secant squared x minus 1. So once again, if the power of tangent is odd, our approach is to pull off one tangent and use the Pythagorean identity to rewrite the remaining tangents in terms of secant. Now note, it's possible to have an odd power of tangent, but not have this extra secant to help play the role of du. But what I want to note in that case is, even though what we see above doesn't apply directly, the idea can be applied. So let's see what we can do. And before digging into this specific example, I do want to make kind of a general observation. When it came to integrating powers of sine and cosine, it worked out extremely nicely. There is a dichotomy. Each and every integral of that form fits into one of two possible cases. Either a power of sine or cosine is odd, and we have an approach, or both the powers of sine and cosine are even, and we also have an approach. Unfortunately, with tangents and secants, it doesn't fall out quite as nicely in the sense that something like, say, tangent cubed doesn't immediately fit the pattern we see above. But hopefully what we can do is apply that same method. So let's see if we can do it. Let's pull off a tangent, and we'll write this as tangent squared times tangent. And then we will rewrite the remaining tangent squared, just like we've done above, in terms of secants, using the Pythagorean identity. So secant squared x minus 1 times tangent. Now note the key difference. We do not have this secant above that would help us play the role of du. So that tells us we're going to need to come up with another approach at this point. But we followed the template. It gave us a starting point. One thing we could do algebraically is simply take this tangent and distribute it through. And I will also note there's not one right way or wrong way to evaluate. There's actually many approaches that can be used in a problem of this form. So we would have secant squared tangent minus tangent. And the observation we can make is we've integrated tangent previously, so as long as we could integrate secant squared tangent, we'd be good to go. So let's break this up into two integrals and go ahead and evaluate. We would have the antiderivative of secant squared tangent minus the integral of tangent. And let's focus in on this first integral. How should we evaluate it? What is your recommendation? Notice the derivative of tangent is secant squared. So this is actually ideal for a substitution. If u is tangent, du is secant squared dx. So we have our u, and then the secant squared x dx combine together and give us a du. So our initial integral can be expressed as the integral of u du. We anti-differentiate 1/2 u squared, and we resubstitute in tangent. And what remains is taking care of this second integral. And what I want to note is it's an integral that we've actually evaluated previously. The antiderivative of tangent is minus the natural log of the absolute value of cosine, which we can get by using a substitution. So I'm just going to note that this is something that comes from our old material. And then just go ahead and rewrite this, plus the natural log of the absolute value of cosine x. And we do rewrite these things at each and every step. So once again, the big observation with this example, not in easy integrals. Anti-differentiation in general is something that can require a bit of innovation. We may have to try multiple attempts before we get it. But sometimes having a starting point is all we need. In this case, if we rewrite tangent cubed, because it's an odd power of tangent, by saving a tangent and rewriting the remaining tangents in terms of secants with the Pythagorean identity, it turns out to give us an approach. Now remember, if you've evaluated this differently, there's many ways to go about it. This is a way that works. Let's move on to the final example to see something a bit more subtle, but it will give us a common anti-differentiation formula we will encounter again in the future. So in this final example, our goal is to come up with an anti-differentiation formula for secant. And as we just mentioned, sometimes the hardest part is getting started. And in this case, we're given a very nice and generous hint. Multiply by 1 in this fancy way. And it's probably not obvious why we are multiplying by this quantity, but in a moment, I think it will be a bit more apparent. So we're multiplying by secant plus tangent over secant plus tangent. And one thing we can do is go ahead and take the secant and distribute it through the numerator. So turn this into just a fraction. And as I distribute the secant through, I'm going to change the order that I'm adding the terms in the numerator. And you'll see why in a moment. So let's write it as secant tangent, that second term in the step above, plus secant squared, the first term above. And our hint is once we've done this modification, let's make an intelligent substitution. And at this point, if you have not solved the integral yet, I would like you to pause the video and give yourselves a couple minutes to try a substitution or two and see if you can make it work. The key observation I'm going to make is that the derivative of secant is secant tangent. The derivative of tangent is secant squared, which is awfully convenient. If we let u be the denominator, secant plus tangent, its derivative is precisely the numerator, secant tangent plus secant squared. So our integral immediately becomes 1 over u, and that's something we can evaluate. The antiderivative of 1 over u is natural log absolute value of u plus c. And then we simply resubstitute. And as I indicated, this is a challenging integral. I don't expect someone to look at this and just immediately off the top of your head come up with this approach. But what I do hope is that when we see the approach kind of step by step, we can follow through and understand what is going on. And furthermore, now if we ever encounter the antiderivative of secant, we have a formula for it. So add this formula to your list of common antiderivatives and feel free to use it when needed. And that completes our current discussion. And of course, what remains, as usual, is just more practice. This would also be a great opportunity for you to go to the textbook and begin practicing suggested problems. And do not hesitate to reach out when you have questions. So stay tuned and take care.